Okay, so let's move to the first case. Okay, remember this case is we're going to use it as a standard practice. Okay, as I mentioned, these are applications that rarely you're going to find, in actual real life application, industrial applications. But the discretization schemes and how we are going to choose on the relaxation tolerances are standard practice that we can use in normal cases, okay? Because we're solving exactly the same terms in the equations like convection, diffusion, solstice, or gradients, okay? So let's move to the first case, okay? So let me present you this case. So basically what we're going to do, and let me here, I'm going to show you what are these on the relaxation factors. So we're going to focus here in this general transport equation, okay? So remember from this equation, you can derive the Navier-Stokes equation. So the treatment now that you're going to do for each of these terms is exactly the same as if you were solving the full Navier-Stokes equation with turbulence modeling. So here we have the problem formulation, we have boundary conditions. So here you have a uniform field. Okay, we have the transported quantity phi here at the end is 1. Here you have the Newman boundary condition, okay, dimensions, diffusion coefficient 0, and a source there. Okay, with these boundary conditions and physical properties and initial conditions, this problem reduced to this governing equation, which have an analytical solution. Okay, so this is the beauty about this, that we can test our numerics in this simple problem that we know the solution. So we're going to see that here we're eliminating the time derivative. Remember, this is a huge approximation now that we use in CFD to get fast outcomes with results that are very questionable, okay? However, if you follow good standard practice and you know what you are doing, you're going to get good accuracy. So the big question is, if you erase these derivatives, how do you advance the solution? So those are the under-relaxation factors that are used to advance solution. So see that here we see the influence of under-relaxation factor in the solution. We know that the solution at the audience is 1. You have it here, and see that in these two cases you have here different solver tolerances, 0.01 and 0.001. So see that in this case with large tolerance, see that different on the relaxation factor give you different values, but also different number of iterations, okay? So if you have larger tolerances, you're going likely to have more iterations, but more accuracy. And this is what you see here. A low tolerance, see that how far from the actual solution you are, okay? And as you keep increasing your under relaxations, see that you are getting more accuracy, okay? So low under relaxation with low tolerance, you are losing accuracy. But as you keep increasing, fixing that tolerance, and you keep increasing the under relaxation, you get more accuracy. And see that under relaxation also you gain speed, you run faster. But this doesn't mean that large under relaxation will be always stable. So you have to be careful that very high under relaxation, they can be oscillatory. Okay, so you said under relaxations are limited between 0 and 1. In this case, see that we reduce the tolerance to 10 to the -3, and see that now even for low under relaxation we have a good accuracy. Okay, it's also 0.991 I think, but see that 0.3 we're already there, and 0.9 see that where you are. Okay, so this is very important. You see that high value is only a pretty picture. Okay, it's not an accurate solution, and you start to get accurate solutions of about 10 to the -3, and that is why you see always in Fluent this 10 to the -3 is kind of an industrial standard, and also in any solver you will see that they propose this value for initial residuals. Okay, and here we see a different behavior. So now here we're fixing on the relaxation two values, 0.1 and 0.1, and we change tolerances. So see that, for instance, 0.7 that should give you better results, but see that when you have large tolerances, small values 10 to the -2, you lose accuracy, okay? But it's not that bad. But then as you keep increasing that tolerance, lower values, let's say, you get more accuracy, okay? So this is the influence of under relaxation, okay? give you more stability and more accuracy. Very important in steady simulation. This is how you control the steady simulations. And by the way, if you have a steady simulation, you can do animation and stuff like that, okay? That doesn't mean that you don't see that one. You can do your normal animations, but you don't have anymore that time derivatives. No, you are not anymore time accurate. So you can also solve this problem using the time derivative, okay? But it will take longer, okay? We are going to see this. So now that I explained the problem, let's go on, open the case. So you download the cases, you will see that, okay, it should be here. You will find this case, the Fluent where if, and as you enter here, you have the case setup. Everything is predefined. There is no need to do mesh. And here you have the solution, okay? So you can plot it in Fluent. So let's open this case and let's explore. So it's a 2D. Here you need to go with 4 cores. So put one that probably 4 cores or 2 cores. We'll let it all down. This is a very small mesh. So let's launch and let's run this simulation. So here we're going to see fast the influence of under-relaxation. And even I'm going to show you over-relaxation, because you can also over-relax. You can put those numbers, the where if larger than 1, okay? So yes, you will go faster, but it will diverge. And I will show you how Fluent diverge, okay? Or how you lose accuracy as well. So here we open Fluent. Okay, now let's read the case. Okay, I'm ready here. I'm reading the case. And we have everything. So here you have the case setup. So let me go through the case setup. So see that steady models is in basic physical properties. As you enter here, you define, you see the diffusivity coefficient for the scalar equation. You put it to 0. And remember that you define the positive scalar or the general transport equation here. User define a scalar and we are defining one equation, okay? So you are defining everything, and to define the source term, so you go here in source condition and enter here, and see here that you have many options, and see that you have source terms. You go here, here's where you can define source term. So see that you have mass, momentum, and you have here the source term for the passive scalar, now the scalar that you define there, which is the general transport equation, okay? So see, you define the value 1. So see our problem definition basically is this one to 1, this one we set it to 0, and now we need to set out the boundary conditions, okay? So you have your problem definition there. Now you go boundary conditions, go to the patches, so you have the inlet patch, velocity inlet there, and see that we're setting this value there, and see that now you access here the user-defined scalar, specify value 0, okay, according to your problem definition. Then you have the outlet, okay, and specify flux, okay. Specify flux is the derivative, is the Newman boundary condition. There is slash Newman boundary condition. So here specify value, there is slash specify value Newman, and then the rest symmetry. So you have your boundary conditions, nothing to do here. Now you go into methods, and here you have many methods, okay? So here, this case is super fast, so you can play with different methods, and you will see that some of them are more efficient, okay? So it's up to you. In this case, it's okay to use any method, okay? It's a very simple method, so let's stay with this method, simple, okay? This is how you couple how you solve your equations, that actually we're not using this. So then see here that how you discretize each term appearing in your governing equation. So see that you have time derivative, convective term, diffusive term, source term. See that here you have a gradient, the Laplacian expressed with. So this see here, this is a gradient, and this here, you are not using these two because we're not solving this equation. Here you are solving this equation, and we want a second order accurate solution, okay? So you define gradients and the US scalar, and this is important, okay? Because here we only want to solve one equation. So as you go here into equations, see that you have the option. So by default it's like this. You are also solving flow equations, Navier-Stokes. So deselect this one and you are only solving this equation. So this is the equation that we're solving. No Navier-Stokes, nothing, okay? So you can also implement new equations in Fluent. That is advanced, I'm not going to topic, but we solve these simple equations, and see here that here's where you have the under-relaxation factors, okay? So I recommend you to go always with the default values, okay, that Fluent proposed, but see that user scalar here, this is the under relaxation, is proposing 1. I don't recommend you to use 1, it's too large, okay? So usually I like to use at most 0.8. Okay, so it's up to you, but play around in this case. So see what happens when I put 0.5, okay? Now, I go here, initialization. By the way, here you have the monitor. I put some monitors to monitor, no, to sample the solution, the outlet that I know is 1. And let me run this case. So by the way, I also put an animation. Okay, so see that you see how this solution is evolving, and see what is happening here with 0.5. See that we arrived to this value. This is a very good solution, okay? And we're using this tolerance. Okay, this is a good tolerance. This is an industry standard. But see what happened when I increase the tolerance here. So now let me rerun, initialize again, okay, and calculate. So now I'm putting a larger tolerance, and see that the problem converges really fast, but see that how far we are from the actual solution. Okay, so it's very important, okay, to use a good tolerance value. As I mentioned, 10 to the minus 3 is a good value. Okay, these 10 to the minus 2, these are pretty colors. These are good, accurate solutions. Okay, so now I can increase and see that now it's getting better convergence. Okay, and you can do even better. Okay, so now you go back here in controls, and let me to show you, put a low value, 0.1. So remember, 0.1, it will give you more stability. Okay, no doubt about that, but it will be much slower. Okay, so if I run now, see that previously it converts in a few iterations. Okay, like, and see here how slow it is. So here it's very stable, but you are slowing down all your computations. Okay, so it's always a compromise, okay, between accuracy and solution speed. Okay, so it's still running. So let's see how far we'll get, and it should get to a pretty good value. Okay, so here it will arrive to. So in this case, see that 0.91. So it's a little bit far, but it's getting closer. Okay, so now if I go again, you can, for instance, see one more accuracy. Let me go and reduce an order of magnitude here. And see that now it's iterating and it's getting closer to the solution, which should be 1. So see that this is already acceptable value. So see that usually low under relaxation is very stable, but you need to reduce your tolerances to get extra accuracy. Okay, and here you have the residuals. Okay, so now let me run the same case, and let me put a large under relaxation. Or let me put 1 that in this case will work. Okay, let me go back to the industry standard, 0.03. Okay, let me initialize here, and let me go here. So see that in just 4 iterations, basically you have the analytical solution 1. Okay, but be careful that this is the section that rather than the rule. Okay, in reality, when you have your full equations and your Stokes and all the turbulence models, here you shouldn't put 1, because that one it will be very unstable. So as I say, I recommend you to have 0.8 or 0.7. So usually I use 0.7. Okay, so usually you will set up like this: pressure 0.3 and the rest 0.7 and 0.7. So this is a good setup for the under relaxations. Okay, here you are not using this one. Remember that we disable the flow equations. We're only solving for this one. And now just to show you that also you can over relax, and just to show you how Fluent diverge. Okay, so let me go here. Okay, and by the way, let me keep running this one, and let me reduce this tolerance a little bit just to show you something. Okay, so see that your scattered residuals are going down, okay, until it reach your tolerance, and you have perfect accuracy. But let me go and let me show you the over relaxation. So to change the over relaxation, by default, Fluent, you see that doesn't let you put values larger than 1, like giving you the value. But as you go here to the text user interface, you can change that value. This is just to show you this is not a practice. This is something that you should do. Okay, you should avoid at all costs over relaxing. But just to show you, you go solve, set. You have there under relaxation, and I want to change this under relaxation. Okay, 0, and let me put there 1.5. See that now it will take it. Let me go back here. Okay, initialize, and let me run this case. Okay, see that now Fluent is divergent. Okay, see that this value is super large value. Okay, so see that how a solver diverges. Even commercial software, if you know what you're doing, you can make it a diverge. Again, this is not a standard practice. Please avoid this one, but I just wanted to show you. And this is when I talk about unbounded solution. This is unbounded. Okay, this is a bounded solution that it shouldn't be larger than 1. See that it's becoming unbounded, and it's just because you are not controlling this under relaxation. You will, if you change this, nothing will happen, and still you will diverge. The problem here is this, okay? And something similar will happen when you have the full sets of Navier-Stokes equation, okay? If you have values too large, it might happen that these quantities will start to oscillate. So that's why control this one. Use the defaults. If you see problems, reduce, never increase it, just reduce it, okay? So let me go back here now to 0.8, initialize. Okay, and if I run, so that everything is okay, I reach convergence. And if I disable this convergence, just to show you, and I will let it run for a large number of iterations, and this is something interesting. See that how your residuals are going down. So this is clear indication of steady solution, but see what is happening there. Now those residuals start to flatten. And this is something, believe it or not, a lot of people ask me question, worry, why is that happening? Remember that in your computer you have a machine precision. At this point, you have reached machine precision. Okay, so cannot go below this. Okay, and this is why I don't like to work in single precision. Remember when you open the solver and you have the options, double precision. Double precision, you can have up to 17 significant digits, no decimal point. In single precision, I think what we call the maximum value is 7. Okay, so if you run the same case in single precision, here the residuals will stall, and it will happen that many of these residuals, they need to go below that 10 to the minus 10. In particular, if you are solving the energy equation, you need to have very well resolved values. So that is the problem with single precision. It's very likely that you are going to lose accuracy, okay? Not in all problems, but in some cases you are going to lose accuracy, okay? So I invite you to now to close Fluent, reopen, do not select the double precision option, and you will see that this will stall here, okay? So this is all. You see, very simple example. I hope now that you have the idea about the under relaxation, how do they work. The other thing that I recommend you to do as an exercise, enable now the transient and run in transient. Okay, so now transient is still in transient. You can use under relaxation. Okay, so under relaxation will help you to stabilize the solution, but remember that now in transient you are controlling everything with the time step. So now you need to choose the right time step, okay, according to a target CFL number. So good accuracy, very good accuracy, I have to say. CFL 1 up to 5 is something accurate. More than 5, you start to lose something. Okay, so play around with this case in time with you having the time derivative. Okay, again, for time derivative, see here that now you need to give the discretization for this term. Okay, so you have different methods, so play around. So in this case, if you decide to do it, you're going to have this equation and this equation, and also gradients. So that's all for this case. See you in the next video. Bye.